Okay, let's pretend I'm an ice skater, okay? And I'm one of those ice skaters that's really good at pirouetting. I'm not because I'm old and I don't have as good balance and I get really dizzy. But if I'm doing this, right, even though I'm not moving translationally, even not moving from place to place, so I don't have kinetic energy that way, you can think of all the points on my body except the ones in the very middle had kinetic energy. My shoulder moved around to here. It had a lot of kinetic energy. Right? If we add up all the parts of the kinetic energy of my body had a different kind of kinetic energy. My center of mass did not move from place to place, right? But my particles all were moving around. So this is a different kind of energy, kinetic energy that we talk about when we talk about rotating objects. And we call it rotational kinetic energy. Okay, rotational kinetic energy. So in my classes, we talk about U, potential energy, we talk about kinetic energy, and we talk about kinetic energy that's rotational. We also talk about spring potential energy, things like that. But what I want to deal with these three mechanical energies to talk about conservation of energy. And I want to level that just a little bit. It looks like an old 1960s Batman film. So we talk about conserving now these three types of mechanical energy. Another way to think of this rotational, somebody's spinning on the ice. If you want to stop them, you have to do work to stop them. So definitely there is some energy that you had to take away by doing work on the system. But I want to talk about a ball rolling down a ramp. Because we always did problems where it was a block sliding down a ramp. We specifically stayed away from balls rolling down ramps because the conservation of energy there is a little different, okay? So here's the ball, and it's rolling down a ramp. And let's just say, I'm gonna call that my 0 point, my zero height, h equals 0. And this is, let's say, 2 meters high, okay? And it's 2 meters high, and this ball has a mass of 0.1 kilograms. And I want to find out what its velocity is down at the bottom. Okay. Now before, what we could do is we could say, okay, U plus K equals total mechanical energy at the top. If there's no work done on the system from outside, the total energy is conserved. U plus K equals the total energy at the bottom. Okay, if it starts from rest, kinetic energy is 0. Potential energy is M times G times H relative to this point. So 0.1 times 10 is 1 times 2 is 2 joules. Total energy is 2 joules. Yep, that's the same down here, 2 joules of total energy. At the end, it's at mgh equals 0, so the potential is 0, and the kinetic is 2 minus 0, which is 2, equals 1/2 mv squared. So 0.05 v squared, and I don't even think I have my calculator down here. So you're just going to have to trust me on that one, that it ends up, you are able to calculate the v, okay? So 4 divided by 0.1, 40 square root of 40, I'm going to say that's 6.3 something meters per second. Okay? Now what we're going to do is we're going to say, well, that's great if it slid. But think of, at the bottom, this assumes that all of that energy turned into linear kinetic energy. But that ball is rolling. It has a rotational kinetic energy. So this, it can't all be kinetic. If it were a block sliding on a frictionless surface, no problem. But now, what I need to include is rotational kinetic energy. So now we have 3 kinds of energy. So the potential is still 2 joules, right? The kinetic translational, I'll just call it translational kinetic energy, is 0. And the rotational kinetic is also 0 because it's not rotating. It's at rest at the top. So the total is 2 joules. Okay, that looks pretty familiar. We come down here, total is 2 joules. The potential is 0. So we have kinetic and rotational kinetic. This is 1/2 mv squared, and this is 1/2 times I times omega squared. Okay? 1/2 I omega squared. Well, it looks like we've got too many variables, except for one thing. We've got the mass. I is a function of the mass and the radius. So we'll have that if I have some more information about that ball. And V and omega are related by the radius. Linear equals R times the angular. So what we can do is we can write, let me write this out the way I would do it as an equation instead of like this. I want to show how these things balance. So now you can see that 2 joules is kind of split into this part. Some of it is translational, some of it is rotational. Well, if some of it is rotational, translational can't be as high as it was before, right? Some of that energy had to go into rotating it. So the translational, the speed of it is going to be smaller. So let's see how that looks in an equation. So what we do when we're solving conservation of energy problems, ET prime is equal to ET. U plus K rotational, I'll just call it R, equals U prime plus K prime rotational. U is, I'm not going to go through the whole thing, MGH plus 1/2 MV squared plus 1/2 I omega squared. And what we end up with is MGH is 2. Okay, but let's spend a little more time on this. This one ends up being 0. These two are 0. Okay, kinetic energy at the bottom is going to be 1/2 mv. And let me skip the primes on this. Just remember that this is v at the end squared. Rotational is 1/2 I omega squared. But remember that v and omega are related like so. So I can substitute this as 1/2 mv squared. For the omega squared, I could call it v over r quantity squared. Now I, if it's a ball, the rotational inertia is 2/5 mr squared. Well, look at that. R squared, the R squareds are going to cancel. I'm just going to take that out because that V remains squared. The 2's cancel there. So we can rewrite this as 1/2 mv squared plus 1/5 mv squared. Okay, if you don't trust me, write it down and do the algebra. But that's what that looks like. Well, this and this we can add together. Let's put them over 10. This is 5/10. This is 2/10. This ends up being 7/10 mv squared. And that all equals 2. Now let's remember, before, this term was not there. Okay, it was just this. So instead of having 1/2 over here, now we have 7/10. 7/10 is bigger than 1/2. When I divide it, I'm going to get a smaller velocity. I don't know if I can do this in my head. 20 divided by 7, mass was 0.1 v squared. 20 divided by 7 is 2.8, let's just leave it at 2.8, equals 0.1 v squared divided by 0.1. So v equals square root of 28 point something. Okay, this is going to be 5 point something. So you can see it's not going as fast as it would be if it were just a thing sliding down a frictionless ramp. And, you know, part of that is, well, yeah, what made it rotate? Friction. If there were no friction, it wouldn't have rotated. Okay, so there, you would expect Newton's second law to tell you that if you have friction in this direction, mg sine theta in this direction, you're going to get a smaller acceleration. And so at the bottom there, we end up with a smaller velocity. So that's how we use rotational kinetic energy. We use the basic equation here, and now instead of just going u plus k equals u prime plus k prime, now we have these three things that we have to add together. So this is part of what we could use for calculating. You'll see problems where it rolls down a ramp, then rolls along a flat surface and maybe compresses a spring, things like that. And now we've just got this new type of energy that we have to include, this rotational kinetic energy. No harder than it was before. Well, I shouldn't say that. You still have to substitute in your I. You need to know the equation. For a ball, it's 2/5 mr squared. And you do have to substitute V over R. Otherwise, you've got too many unknowns to solve this problem. I think that's all I really need to talk about on rotational kinetic energy. I will just say that when you see a ball on a ramp, always remember that you're going to have that additional type of energy. Usually when you've got the ball on the ramp, that is the kind of analysis you're going to have to do, is the energy conservation analysis.